Thank you, Rod, and thank both you and Jeff for inviting me to speak. I have no medical background that I may give myself away by pronouncing something wrong later. My formal training is in mathematics and theoretical computer science, and I've also done some research in the cognitive sciences. I am a programmer and a data scientist using machine learning, but I have been studying the ketogenic diet informally for about 20 years and following the literature. So the only disclosure that I have is that I do have an account on Patreon, and I have some generous supporters there who are supporting my writing. But I write a blog and I'm writing a book, and my donators don't get anything that is not going to be public content. The foundation of much of our biochemical understanding of ketosis comes from experiments in fasted humans and animals. Particularly the work of George Cahill has been very influential. He recently, or relatively recently, published a paper called Starvation in Man, which I'll be using some graphics from. And that goes over a lot of his career and some of his more current thoughts on the issues. The problem that that kind of origin carries with it is an implicit warning, because obviously starvation is not recommended. It's not sustainable indefinitely. It's stressful to the body, and it can have harms that are sometimes irreversible. As you know, even shorter-term fasts are controversial among experts, even among us, and the concerns come down to potential damage to lean mass and all of the potential dangers of protein and calorie malnutrition. And so if ketosis is like fasting, then it sounds like if we're going to use it, we'd better use it judiciously and sparingly. Researchers like to conceptualize metabolism as having these two complementary phases, sometimes called the fasting state and the fed state, or the anabolic and catabolic state. This paper came out in January, and the researchers are calling it the glucose state and the ketone state. And both of those phases are important. In the fed state, we're doing things like synthesizing proteins in tissues, biogenesis of mitochondria and neurons. And in the fasting state, we're doing renewal and repair and tearing down broken structures. And we're also providing the stimuli that direct the body of what kind of tissue to build when we do go back into the fed state. Many researchers feel that if you stay in any one state too long, you're going to lead to some kind of disease. In ketosis, therefore, we might think that if we're in it chronically long term, we're setting ourselves up for some kind of problem. And to make matters worse, if you look at the research coming out of the longevity studies, we notice that some animals use signals of the fed or fasting state to determine whether we're going to be reproductive and full of vitality because there's a lot of nutrition in the environment, or rather shut down reproduction and wait and try to extend our life so that we can be there when the nutrition comes back. And so this exacerbates our fear that even though ketosis might be showing us some benefits, it's coming at a severe cost. But hold on, starvation isn't the only time in nature that ketosis happens. It just so happens that fetuses use a lot of ketones. The placenta is full of beta-hydroxybutyrate. Many mammals have the ketosis of suckling, including human infants who are in ketosis. And in fact, humans of all ages, as long as they're not eating very much carbohydrate, they don't have to be in a protein or calorie deficient state to be in ketosis. This graph shows the level of beta-hydroxybutyrate after a certain amount of time without eating. What's most stunning about it, I think, is the orders of magnitude involved. So if you look at the children of 6 to 8, after about 4 hours, they're maybe only at about 0.1 or 0.2 millimoles. But before the day is out, that's gone up by a factor of 20 or 40. Newborns who aren't having cereal yet don't even start that low. And you'll also notice that children don't need to go a whole day without eating to get into ketosis. Of course, they don't have to stop eating altogether. This is from Eric Kossoff, who spoke earlier. And the classical ketogenic diet is very protein restricted and restricted in other ways, but we also now know that children with epilepsy and adolescents who are on the modified Atkins diet, which basically means you don't increase carbs according to weight loss, typically are in ketosis, even though their protein is not restricted. And they're growing. This is a growth state. So without the protein restriction that we had in the classical ketogenic diets, the growth doesn't seem to be impaired. Even adults are able to stay in ketosis with enough protein to meet all their needs. How much protein we really need depends on who you ask. The RDA will tell you only need about 0.8 grams per kilogram, but if you read the reference document that goes along with their recommendation, even they admit that that's really not enough for everybody. We can look at studies in protein-sparing modified fasts, and so that's a question of trying to find out the very minimum amount of protein that you can give to obese people who are losing weight so that they're staying in positive nitrogen balance. And they found that females need about 1.2 grams per kilogram of ideal weight, not their current weight, and men 1.4. And there was a recent blog from the Verta Health Group saying that maybe it's actually 1.5 to 1.75 grams. We don't have, as far as I know, a systematic study that had the express purpose of finding out how much ketosis above that minimum you can actually go and stay in ketosis. But I did find this collection by Adam Tsur that recorded from other studies what the level of ketosis and level of protein was. Keep in mind that a lot of these studies were done in overweight people, so that gram per kilogram is not of ideal weight, it's of current weight. So for example, in the second line where it's 1.1 grams per kilogram, the people in that study had an average body weight of 108 kilograms. So maybe it's closer to 2 if you look at the ideal weight case. In any case, all of this is suggestive that the amount of protein you could eat is not only just the minimum amount, but maybe even 1.5 or 2 times that amount. It's all the more impressive when you look at this from the point of view not of comparing adults to children, but comparing adults to other species. Dogs are fairly similar to us physiologically, and they do get into ketosis when fasting, but it takes them a little longer, and they don't get ever into the deep range that we get into. And then if you give them enough protein, it essentially vanishes. I was speaking with some staff at the Keto Pet Sanctuary, which is a clinic that treats dogs who have cancer with ketosis, and they told me that they need to restrict calories, restrict protein, add MCT oils, and constantly monitor and adjust to keep dogs in ketosis. We often use rodents, and I think they make a good model, and it's very useful, but we have to keep in mind that it does take either protein restriction or calorie restriction or a bit of both to get them into an adequate range. And once again, the range of ketosis is not nearly as spectacular. And similarly, if you give them any amount of carbohydrate, the effect virtually disappears. Researchers think that this has to do with their brain size, because after all, one of the ideas we have about the function of ketosis is to spare glucose for the brain, and if they hardly have any brain, then you give them a little glucose and they don't have the need anymore. But it turns out that glucose or ketones isn't the only way to get energy needs met for the brain. If you look at obligate carnivores, you might think in their natural state in the wild they're eating a low-carb diet, so shouldn't they be using ketones all the time? Well, it turns out they hardly do at all. They're specialized for gluconeogenesis. Cats, in fact, if you fast a cat, they don't seem to have a way to really cope with the protein amino acid deficiencies and vitamin deficiencies. So they have problems with methylation, they have ammonia toxicity, and oxidative stress. And quite surprisingly to me, although they do produce ketones, they don't seem to be able to use it productively. Cats who are fasted actually develop fatty liver. So that's the opposite of what humans do, right? So they seem to be more like a dangerously type 2 diabetic human where there's too much glucose and ketones and fat and they don't know what to do with it all. Dolphins are also interesting, you'd think, because they do have larger brains that maybe they would be the ones who would show ketones. And in fact, unlike cats who do produce some, they don't seem to produce any at all. So carnivores meet all of their needs for their brain when they're not eating by just ramping up gluconeogenesis. When faced with this difference between species, I think the first question that occurs, well, to me is, well, how is that happening? What's the biochemical mechanism? And I don't know, and I didn't find the answer in the literature. And I'm not a biochemist, and I'm not in a position to try to test out my theories, but one hypothesis that I did have was that it comes somewhere in this CPT carnitine system. So Ben Beekman talked about carnitine. It's an enzyme that upregulates CPT1. CPT1 allows transport of fatty acids into the mitochondria. And so another coenzyme that's involved in the process is malonyl-CoA, but it's inhibitory. Malonyl-CoA goes up as a direct effect of glucose oxidation, and it's on its way to lipogenesis. So you could think of malonyl-CoA as being a switch between lipogenesis and lipolysis. It kind of makes sense that you don't want those turned on at the same time because that would be a little bit inefficient. But on the other hand, there has to be a little bit of hysteresis, right? Rob Wolf talked about hysteresis on the other side. I think about hysteresis with the analogy of a thermostat. If you set your thermostat to 70, you don't want your heater to come on when it drops to 69.9 and then turn off again at 70, or else you'd just be thrashing all the time. So you let it go a little bit too far below, and you let it get a little bit too far above before you make your changes. So not only does malonyl-CoA inhibit the CPT1 activity, but the less of it you have, the less sensitive CPT1 becomes to it. So if you're already ketogenic and you start burning some glucose, you don't automatically react to the malonyl-CoA and turn off ketogenesis the way that you would if it were there and you weren't in a ketogenic state. Incidentally, this malonyl-CoA and CPT1 are involved in that notorious Arctic variant in the Inuit people. It's not all Inuit people, but the ones who have it have this mutation that drastically reduces the activity of CPT1, and that means they can't get as much fatty acid into the mitochondria and their ketogenesis is limited. And people talk about that suggesting that those Inuit don't have the ability to make ketones. It's not precisely true, but one thing that isn't often mentioned is that the other effect of that mutation is to increase, or rather decrease, the sensitivity of CPT1 to malonyl-CoA. And some researchers are suggesting that this allows the people affected to stay in ketosis longer even if their protein goes up. And another important part about that gene is that it's extremely localized to coastal areas where the polyunsaturated fat intake from sea mammals is way up. And polyunsaturated fat is a lot more ketogenic than saturated fat. And that means that, well, potentially, hypothetically, it could be that having that high level of CPT1 activity in the first place is what allowed them to pay a bit of a cost to get that extra insensitivity. But all that's just hypothetical. I would love it if someone figured out what was making the biochemical difference. The second question that I think is very interesting is what would have allowed this in the evolutionary environment that we developed this trait of extra ketogenesis. At the very least, I think it suggests that we spent a significant amount of time with little access to carbohydrate and a lot of access to protein and to fat, either exogenously or endogenously. And then thirdly, what was the advantage? Why do we use ketosis even when we have plenty of protein, more than enough protein to supply our brain's needs with glucose without compromising our lean mass? Or to put it another way, other animals continue to burn through lean mass even though all the way until they can fuel everything with glucose. So what makes that difference? I think it has something to do with the brain. There's a little hint there. But of course, I don't really know. I wasn't there. But I'll suggest some reasons why the brain might have been the key to that advantage. We have really big brains. Primates already have big brains compared to other mammals, and ours tripled in size compared to that. And the brains take a lot of energy at the same time that we tripled our brain size. We also lost intestinal tissue. Scientists think that that is because intestinal tissue is very expensive to maintain, and so in order to allow the extra energy to free it up to make brain tissue, we gave up some of our colon tissue. And then that in turn made us more dependent on animal-sourced food because now we couldn't ferment so much fiber into fat. So the brain takes a lot of energy. A human adult brain uses about 20% of all the energy that we're using in our brain. A little bit of that needs to come from glucose, or at least does come from glucose, even when we're fasting, but the rest can be done with ketones, and there doesn't seem to be a limit to how much we'll take up in the brain. Whatever's floating around, we'll take it up proportionately. Now, if you think adults have big brains, how much bigger is your brain if you're actually a baby? And so how much more energy do you need? Well, some people think that this is the explanation for why human infants are so fat. These graphs are from a paper that's exploring hypotheses about body fat in infants. It turns out that human infants are way fatter than most other species. We come in at about 15%, the graph on the left. The token great ape in there is the baboon at 4%. And then the graph on the right is showing that proportion of energy that's being metabolized in the brain. The adult human at 20%, but the adult infant at 60%. And the token great ape on that slide is the chimpanzee at 9%. So another kind of hypothesis of where the selective advantage would come from is structural. Our brains are made out of cholesterol and fat, and it turns out that we do that in situ, and we make it out of ketones. The pathway on the right shows the way that ketones are made into cholesterol and fat. And it stands to reason that if children are having a higher level or higher ability to get into ketosis, maybe it has something to do with the fact that they're developing their brains. Our brains are growing past weaning, so other mammals that might have ketogenesis of suckling, their brain's growth stops when they wean, but our brain growth doesn't stop when we wean, and even when the size stops growing, the structural changes go into the 20s. However, quantitatively, the cost of those structural components is not very significant compared to energy, so this hypothesis on its own is maybe a bit weak. A third hypothesis, which is actually really very many hypotheses, is just about the different kinds of metabolic effects that happen inside the brain when you're on a ketogenic diet rather than a high-carb diet. So some of those effects would be higher ketone bodies, which themselves have effects, reduced glucose, increased uncoupling proteins in mitochondrial biogenesis, decreased radical oxygen species, and increased glutathione, which have oxidative stress consequences. There are changes to neurotransmitters in norepinephrine, GABA, glutamate, and adenosine. And then one that people don't seem to talk about very much is the increased plasma availability of free fatty acids, including DHA and arachidonic acid, which are very important in the phospholipids of the brain, and they're in flux, so we want to have a constant supply of those. Each of these, I chose this list because each of those has been proposed over the years as an explanation for why ketogenic diets are so effective in the treatment of epilepsy. But epilepsy, of course, isn't the only thing that happens in the brain. It's just the one that we have the best research on and the most widest acceptance. So we have preliminary evidence, at least, that a ketogenic diet can help in neurological degenerative diseases. We have animal models where we know that if we put our animals on a ketogenic diet, they will have greatly increased survival in the face of stroke or trauma or even nerve gas. Cancer and the treatment of the role of ketogenic diets is one of those controversial things, but the best evidence that we have for a positive effect comes from brain cancer. And I just also want to bring up mood disorders and psychiatric conditions, as Georgia Ede talked about a lot, and there are a variety of mechanisms that could contribute to that. So I almost want to call a ketogenic diet a brain growth mimicking diet. This question of how and why humans are different from other species in their prioritization of ketogenesis and actually the sort of reluctance to give it up unless we're taking in so much glucose that we need to store it. seems like it could lead to a lot of insights. And I do think that it probably does have a lot to do with the brain. Just to return to the metabolic switching idea. So one thing that's glossed over in this dichotomy of the fed state versus the fasting state is the post-absorptive and absorptive state. If you're on a high-carb diet, it takes about 4 hours for you to deal with all the incoming glucose. And that stage where you're doing that is called the absorptive phase. And after that, it's marked by changing from the exogenous glucose to the drawing from your glycogen stores. If you're on a standard American diet, you probably don't go more than 4 hours while you're awake before you start eating again. So you hardly get into this post-absorptive phase at all unless you're sleeping, and maybe if you're lucky, you might start to get into this fasting ketogenic phase. But as this picture from Cahill shows, it tends to take days and days. And so you actually have to fast to get into the fasting state. But if you're on a ketogenic diet, I don't know how long it takes for the absorptive stage to happen in that case, and to be relying, you're almost immediately relying again on your glycogen stores. And your glycogen stores are already less in comparison to someone on a high-carb diet, so you're much farther along that process immediately. If you wanted to accentuate the difference between those stages, you could maybe add some extra demand on energy, i.e. exercise, or you could just wait a little longer between meals, which I think happens quite naturally for people on ketogenic diets, if not intentionally. So I feel like not only is ketosis not detrimental by giving you malnourishment, but it actually allows you to go back and forth between these phases that are supposed to be so important on a daily basis, rather than having to go out of your way to do a kind of intensive therapy where you're not eating for long periods of time. It just seems like it's all quite easy suddenly to get the benefit of both of those states just in the course of your regular life. So I really object just semantically to this comparison of the word starvation in association with ketosis. I think it causes alarm and suspicion and fear where we don't necessarily need it. I think if you're on a high-carb diet, then maybe you do need to do some extended fasting to get to this enlightened brain state that people are after. But if you're just a human on a regular ketogenic diet, then I don't think that's necessary. Thank you.